Okay, recall that increasing just means going uphill, if you're talking to your baby brother. Decreasing means going downhill. So a function is decreasing anywhere its graph goes downhill. Concave up means looks like a bowl, and concave down means looks like an umbrella. So if you consider those two different kinds of behavior, increasing versus decreasing, and concave up versus concave down, then there are 4 possible combinations of those behaviors that a function could have over a certain interval. And I have just a quick little sketch example of each of those. So this top left corner, a function could be concave up and decreasing, meaning it looks like a bowl that's going downhill. It could look like a bowl that's going uphill. That's not great. The picture's better than my thumb, right? Okay. And in each of these graphs, I've just chosen a point. If this is some function f of x, I've just highlighted one single point, x equals a, and I have sketched in the tangent line to f at the place where x equals a. I notice here that all my f's are red and the tangent lines are blue, which is switched from what it was in the last picture. But you guys are okay. You can tell that the curvy part is the function and the straight part is the tangent line. So before we move on to the next slide, can you take a moment and for each of these 4 possibilities write in whether the tangent line lies above the curve or lies below the curve? Obviously it touches the curve in one place, but for the whole rest of the tangent line, does it lie above the original curve f, which is in red, or below? So write them in no. And the place where, if the tangent line lies below the curve, so here's an example, right? The tangent line lies below the curve, then if we're going to use the tangent line as an approximation, all of our answers are going to be underestimates. They're all going to be too low. They aren't as high as the curve, and the curve is the right answer. So in this case, the tangent line is going to be an underestimate. That's what happens here as well. The tangent line is an underestimate, and for these guys, that's an O for over. The tangent line is an overestimate because the tangent line lies above the actual f function. So you can check your answers here. This is a picture with sort of all that information tied in together. So what can we conclude about that? I said in the last video that this video is all about how to decide if your tangent line approximation, which we learned how to do in the first video, this video is about how to decide if that approximation is an overestimate, is that approximation too high, or is it an underestimate, is it too low? So we can conclude, and there's a place to fill this in at the top of the next page of your notes, that anytime that I find the linearization of f at a on an interval of the curve where f is concave down, the tangent line has to lie above. That means my tangent line is going to be an overestimate. So feel free to use, probably have to use the words from your handout. We conclude that the linearization L of x of a function f of x overestimates f of x on intervals where f of x is concave down. So make yourself a bowl for concave down and try to put the tangent line on. The tangent line has to lie above the bowl. So that means the tangent line is an overestimate. And the second part, we conclude that the linearization L of x is an underestimate. It underestimates f of x on intervals where f of x is concave up. And remember, we know a little bit about how to figure out where f is concave up or concave down. It comes from checking the sign of the second derivative. So you can see the extra note we put in here. Feel free to add that into your notes paper if that is helpful to you. So just a caution, I haven't seen this come up specifically, but I'm expecting that you would be able to justify your answer and know this when you justify your answers. To be sure whether your tangent line approximation is an overestimate or an underestimate, you have to be sure about the concavity of f on that interval, and the concavity of f can't change. If there's a concavity change somewhere along there, then your decision about whether your tangent line is an overestimate or underestimate isn't going to hold. And so what do I mean by that interval? It's got to be the interval that includes the point of tangency which in the formula we call A, place where the tangent line touches the graph, and any other x value that you're trying to use as an input. So for example, in the example we did in the last video, we used the cosine function at pi over 2. We used the tangent line of the cosine function at pi over 2 to approximate cosine of 1.75, which is pretty close to pi over 2. So that whole interval between the x value we knew, which is pi over 2, and the x value we cared to compute with later, 1.75, we had to know the concavity on that whole interval. So we did in that case, which is, you typically will, but then you're going to have to make a justification later because I'm going to ask you, is your answer an overestimate or an underestimate? And give a reason for your answer, right? So you're going to conclude that your function, your tangent line produced an overestimate of f of x because f of x was concave down on that interval that includes both the a and the x value that you're caring about. We'll do an example now. All right, let's see how we do here. So just I'll point out that this is from the 2002 free response section. That's one part of like a 4-part question, and notice how many little parts there are within this part. So we're going to make sure we hit them all. We have a table of values for a function f and f prime. We've been told that f is we've been told it's differentiable, so it must be continuous. We've been told that it has a second derivative, and that the second derivative is always positive. When they tell you something like that, you should start to be suspicious that you're going to have to use that. Okay, so we've been asked to write an equation of the line tangent to f at the place where x is 1. We're going to use that tangent line to approximate f of 1.2. We've been asked to decide if our answer, our approximation of f of 1.2, is an overestimate or an underestimate, and we have to give a reason with our answer. So the things I'm going to need to know, I need to know the point of tangency. Okay, I've been told that it's x equals 1. I'm going to need the y value there. That's going to be f of 1, which is -4. I'm going to need the slope of f at x equals 1. That's the same as finding f prime of x evaluated at x equals 1, or f prime of 1. That is 5. So I think I admitted to you in the last video that I don't actually memorize that function in the yellow box. I start with point slope form for the equation of a line every time. But feel free to memorize in the box. That's totally fine. Whatever works for you. I'm going to write y minus y1, which I said was -4, equals the slope times x minus the input value. The x is x1. So this would definitely get a point. This is a tangent line equation, which is the first thing they asked for, right? The equation of the tangent line. I'm supposed to use that tangent line to approximate f of 1.2. At this point, I like to have a function, which means I like to have y isolated on one side. So I'm going to rewrite that. It's not actually technically required that you do. I think it makes the notation a little easier here. So y is going to equal, that was subtracting -4, which means I'm going to have to add -4. So -4 plus 5 times the quantity, x minus 1. Remember this, now that I have y isolated, this is another name for a function that's a pretty close approximation to my original function, which in this case was called f. If you'd like to call it L of x for linearization, that's fine, but not required. -4 plus 5 times x minus 1. And I hope you know, that for places near x equals 1, this function, capital L, is going to be a good approximation of f. That's the same thing as saying that f of x is approximately equal to L of x, which means that f of 1.2 is approximately equal to, if you use an equal sign there, you will not get full credit. F of 1.2 is approximately equal to -4 plus 5 times the quantity, 1.2 minus 1. You have no obligation to simplify that expression, but I'll just point out that if you have so far avoided the temptation to distribute that 5, you'll find that the computation is actually easier if you do the subtraction first. 1.2 minus 1 makes 0.2. So I'm going to say that my f of 1.2 is approximately equal to negative 4 plus 1 is negative 3. At this point, we have the right answer. And as long as there's been no mistake, you're going to be fine. But can I just urge you, take a moment. Imagine you were going to squeeze 1.2 into this table, and you just said that its output is negative 3. Does that shock you? Okay, hopefully it doesn't shock you, because you'll see, well, okay, I had a negative 4, and here's a negative 1. Negative 3 kind of comes in between. That doesn't surprise me. I'm embarrassed to admit to you, but I will admit to you that I just did this whole video with a mistake. I had added 4 instead of adding negative 4 to both sides, and I got the answer 5, and I was like, oh, okay, this is fine. I didn't even notice, because I didn't stop to check that my answer made sense. If I had stopped to check and I had tried to write a 5 into this table, I would have been, that's, I mean, it could happen, but that's not really a great approximation if this function changes from negative 4 to 5 and then back to negative 1. So check your answer. I could have saved myself a lot of time if I'd checked my answer. So here we go. This is the answer to their second question. F of 1.2 is approximately equal to negative 3. Now we have this last question. This answer, f of 1.2, is approximately equal to negative 3. Is that an overestimate or an underestimate of the actual 1.2? At this point, if you had an equal sign there, I hope you stopped and noticed, because we are saying definitely, 100% certainly, that negative 3 is not f of 1.2. So if you have an equal sign there, that can't be right. But we're saying it's a pretty good approximation, but we can say even more. We can say whether it's an overestimate or an underestimate. And how do we decide? Well, we learned at the beginning of this video, it has to do with the concavity of f. So, concavity of f. We've been told that f double prime is positive. F double prime is positive means the same thing as concave up. So you can have memorized those 4 pictures I drew. You can have memorized the top of the second page of your notes. You can, I do neither of those, just so you know. You can make yourself those 4 pictures at the beginning of every AP test and your chapter 4 test. Or you could do what I do, which is, okay, I just figured out that I know F has to be concave up, so I make myself a little concave up picture. Bowl, right? And I say, okay, where's the tangent line? If I try to draw the tangent line to the bowl, where is it? There's no way you can draw that tangent line that is not underneath the original F graph. So I know that since F is concave up, that any tangent line I draw is going to be an underestimate, and that's what I'm going to write up. All right, so here's my write-up. Here's some options you can use here. I had to make up an option for approximately equal to, because I don't have a wiggly equal sign on my program here. So I said f of 1.2 is approximately equal to negative 3 is an underestimate of the true value of f of 1.2, because f is concave up on the interval negative 1.5 to 1.5. So again, you have some options. Instead of concave up, you could have said something that means the same thing, which is what is circled here. You could have said because f double prime of x is greater than 0. That would have been completely equivalent to f is concave up. You could have given a smaller interval. You could have given any interval that is a true interval on which f is concave up, as long as it includes 1.2 and the original x value that you used, 1. So the smallest interval you could have given is the interval from 1 to 1.2. But here I just gave the whole interval because any one is fine. But if the interval that contains, if f is not all one concavity, in this case concave up, on the interval that contains 1.2 and 1, then you cannot make a conclusion, which they probably wouldn't ever do on the test, but you do need to use this interval in your explanation. Some interval that contains at least the original x value for the point of tangency and the x value at which you've been asked to approximate the function.